For a century, the power grid was synchronized by physics. Massive spinning steel turbines locked into the grid's frequency through sheer mechanical inertia. Today, that physical connection is being replaced by silicon switches, voltage source converters. The interfaces for solar, wind, and battery storage have zero moving parts and zero physical inertia. Because they lack that mechanical mass, these inverters cannot passively sync with the grid. They rely entirely on digital control algorithms to actively measure the network and decide how to interface with the AC network. To safely push active and reactive power into the system, the inverter's output must perfectly match three variables of the AC grid: the voltage amplitude, the grid's frequency, and the exact phase angle. While voltage and frequency are observable, the inverter also requires the exact instantaneous phase angle of the grid, represented as theta grid. This value cannot be extracted directly from the raw three-phase voltage measurements taken at the grid connection point. The alternating current is constantly fluctuating, leaving no direct reference point to calculate the exact angle in real time. Because the phase angle cannot be measured from the raw signal, the inverter requires a dedicated computational engine to deduce the angle mathematically and lock onto it. The industry-standard solution to this tracking problem is an algorithm called the Synchronous Reference Frame Phase-Locked Loop, or SRF-PLL. The objective of the PLL is to construct an internal mathematical reference frame inside the inverter's software. This virtual frame is designed to continuously shadow the actual external phase of the physical grid. While it functions as a sensor, the PLL is actually a closed-loop feedback control system. It makes a guess at the grid's phase, measures the error of that guess, and actively corrects its own internal estimates thousands of times per second. Without this algorithm acting as a gateway, it is impossible for a grid-following inverter to achieve stable, decoupled power injection. The entire operation of a modern renewable power plant relies on the accuracy of this loop. The PLL algorithm begins by applying Park's transformation to the raw grid voltage measurements. Park's transformation is a mathematical translation. It converts the rapidly oscillating stationary three-phase signals, A, B, and C, into a rotating DQ reference frame. This transformation is necessary because AC signals oscillate far too rapidly for simple control logic to regulate. By projecting those alternating waves onto a reference frame that rotates at the synchronous frequency, the signals are transformed into DC-like, non-oscillating quantities. This allows engineers to regulate the system using standard proportional integral, or TI, controllers. Translating time-varying chaos into stable constants provides the mathematical foundation necessary to measure and correct phase alignment errors. To achieve synchronization, the controller must align its internal mathematical D-axis perfectly with the rotating vector of the physical grid voltage. When this alignment is perfect, the D-axis voltage equals the peak grid voltage, and the Q-axis voltage, VQ, drops exactly to zero. The PLL exploits a trigonometric shortcut here. For very small phase differences, the quadrature voltage, VQ, is roughly equal to the amplitude of the grid voltage multiplied by the phase error, delta theta. This makes VQ the ultimate error metric. If the controller can force VQ to remain at zero, it guarantees that the inverter's estimated angle perfectly matches the grid's actual angle. To do this, the VQ signal is routed directly into a PI controller. The controller is tuned to relentlessly regulate that specific input down to zero. The output of this PI controller is a frequency deviation, delta omega. This is then summed with the nominal grid frequency, typically 50 or 60 Hz, to determine how fast the inverter's internal reference frame needs to spin. This adjusted rotational speed is fed through an integrator block. Integrating speed over time converts the frequency into the final product, the estimated phase angle, theta prime. Finally, this estimated phase angle loops back to the Park's transformation block to process the next incoming voltage measurement. This continuous feedback loop traps the inverter into an endless cycle of self-correction. By constantly zeroing out the error metric, the inverter locks its internal digital clock to the physical reality of the grid. Maintaining a zero quadrature voltage synchronizes the inverter and decouples the control of active and reactive power. Once the D-axis is perfectly aligned with the grid voltage, the active power injection is dictated entirely by the D-axis current. Meanwhile, the reactive power is managed entirely independently by the Q-axis current. To keep these pathways distinct and stable, control engineers must rigorously tune the PI controller within the phase-locked loop. The closed loop is modeled as a second-order transfer function. Engineers calculate precise proportional and integral gains, Kp and Ki, to enforce a specific damping ratio and guarantee a rapid settling time, usually around 100 milliseconds. When tuned correctly, this decoupled system allows the inverter to operate with high precision. But this mathematical harmony rests entirely on one assumption, that the grid voltage it tracks remains stiff and predictable. The mathematical elegance of the SRF-PLL becomes a liability when inverters are connected to weak grids, networks characterized by high impedance and low fault currents. Small signal analysis reveals a hidden risk. Modes 5 and 6 present highly oscillatory eigenvalues. These aren't from physical hardware. They're governed by the inverter's internal software states. The exact culprits are the PLL calculated phase angle, the PI integrator, and the filtered Q-axis voltage. The exact variables engineered to ensure synchronization are the variables that trigger systemic instability when grid conditions degrade. In a weak grid, high line impedance means that any change in current causes a noticeable voltage perturbation at the point of common coupling. When sudden voltage shifts occur, the physical reference frame tears away from the inverter's mathematical frame, opening a widening error angle, delta theta. The PLL scrambles to close this gap, but its tracking speed clashes with current loops, causing simultaneous conflicting phase and power adjustments. This interference leads to the inverter injecting skewed, misaligned currents. Those errant currents hit the weak grid's high impedance, causing further voltage fluctuations. The result is a destructive cycle of subsynchronous oscillation, where the electrical resonance violently amplifies itself. In a weak grid, the inverter's attempt to chase a moving phase target creates a self-amplifying feedback loop that can crash the entire system. The instability observed in weak grids is forcing the power industry to rethink how inverters operate on modern networks, leading engineers to design architectures that abandon the traditional PLL entirely. Advanced control strategies like virtual synchronous machines and power loop controllers discard direct phase tracking. Instead, they synchronize by mathematically emulating the power flow equations of actual spinning rotors. To guarantee the stability of a grid powered entirely by renewables, the industry must evolve beyond forcing mathematical phase locks and instead design software that inherently emulates the natural synchrony of physics.